are three types of chemical bonding that we're going to look at in general chemistry. The first one is metallic, and in this unit we just need to know how metals bond. We're not going to need to look very in-depth at their qualities, we just need to be aware of their bonding type. Okay? When we get to states of matter, we'll start to learn a little bit more about metals and where their properties come from, and it'll all stem from this type of metallic bonding. Now, if we look at, let's just say, a pile of copper, I've got a bunch of copper atoms all bonded together to make a single copper bar. A single copper bar. How are these sticking together? Right? They're not just single atoms floating around, so how are they staying in place? Well, let's remember copper's electron configuration. There's 1s2 through 3d9. It's this d orbital that's going to do all that magic. Now, the d orbital looks like this. These are the different shapes of the d orbital. We've got these different shapes here. And what happens with these shapes is when they overlap, they really stretch pretty far away from the atom in all of these different directions. Think about 9 electrons have to be spaced evenly around this atom. Well, that's going to result in them being pretty loosely bound to each carbon. So each carbon might have a d orbital that stretches out this way, and the carbons near it are also going to overlap that. And because of this, the electrons in these d orbitals, let's put the electrons in red, those are going to be pretty loosely bound to each of these carbons, being easy to just kind of interchange and interweave. And so that's going to happen throughout this entire metal. And that's going to be what causes these copper atoms and metal atoms to stick together. And so we call this the electron C model. We've just got a bunch of electrons floating around, kind of belonging to no one. I always like to make the joke, this is the socialism of atomic bonding, because everyone owns everything together. No one owns any of these electrons. So we call this the electron C model, because it's like the copper atoms are just connected through an electron C. This is going to give metals all of their interesting properties, like their ability to easily conduct heat and metal, their ability to be deformed, like if I hit a metal bar with a hammer, it's not going to break, it's going to bend. Because these electrons, they're not a rigid bond. They don't need it to be this way. They don't need to have this bond between this copper and this copper. They're totally fine with bending if this side of the metal gets hit. And so they'll bend before they'll break. Now let's look at something that'll break before it'll bend. Let's look at ions. We've talked about ions before. This is when an atom is going to gain or lose an electron, right? So we can have positive cations. So we've got sodium here. This would be our cation. It's positive, okay? And then our chlorine here, this would be our anion. So cation because it's positive, right? Positive. Yeah, and anion because I've never met anyone named Anne who's not a complete pessimist, total negative person. So when we have these ions, well, according to Coulomb's law, remember, F equals, I told you this was going to come up a lot, Q1, Q2 over R squared. Well, because these are opposite charges, they're going to want to attract. And so sodium and chlorine, I've got a 1 and a 1 here, let's just say a positive 1 and a negative 1. And when they get close, they're going to stick together with a great force. And that's what's going to happen in ionic compounds, in ionic bonding. We get these two different ions. Sodium would give an electron over to chlorine, and then they would be very attracted to each other, and they're going to stick together. And I'm not just going to have a single sodium and a single chlorine. I'm not just going to have Na and 1 Cl. I'm going to have a whole pile of these. And so when these get together, well, the sodium is going to be positive to all of the chlorines around it. And so we're going to get these lattice bonds. And so they pile together like this. So all of my NAs are going to be attracted to all of the chlorines near it. And so they're going to connect kind of like a big block of Legos. And when they do connect, they form this very specific ionic lattice. And so we can see this structure takes this very cubic form, right? We've got this very straight cube. And all of these atoms line up nice and perfectly. When we get a large crystal of sodium chloride, this is called sodium chloride, NaCl is sodium chloride, we get these very specific cubic structures of salt. If you ever see a salt crystal, you'll see that it has these very flat planes. And so this is because these ions are all sticking together, forming this lattice in this very exact way. Now, if they have different charges, like, or different shapes, like copper sulfate, CuSO4, well, copper is my cation. It's going to be Cu2+. SO4 is going to be my anion, SO4 2-. Well, SO4 is actually one sulfur and 4 oxygens. Looks kind of like this. And so that's going to be quite a bit bigger. And so when SO4 connects to copper, it's going to make a very different crystal shape. And so we get these ionic substances. They're all going to be really crystalline in nature. And they're going to have these very specific shapes that are going to be completely due to the shape of the individual atoms and the charges of the individual atoms. And we'll look at those more specifically as we learn how to name ions. So our third type of bonding is going to be covalent bonds. And covalent bonds are going to be a little bit different than both the electron C model in metallic bonding and the separation of charges in ionic bonding. Covalent bonding, and let's use carbon dioxide as an example here. Let's go CO2. In covalent bonding, these atoms don't quite give up their electrons. They don't quite take the electrons. They end up sharing the electrons. And so I like to draw this as carbon. Let's say carbon's got this electron orbital, this electron cloud right here. It's going to have one on either side. And then let's say it's got an electron in each of these, one electron. And I'm going to have an oxygen, and this is going to have an electron cloud. And over here, I'm going to have another oxygen. And so that oxygen is also going to be sharing its electron. So the carbon has an electron here. This is the carbon's electron. It's the carbon's electron. And the oxygen is going to have its own electron. Let's put that in green. So this is the oxygen's electron. And so they're going to both be holding on to both of these electrons, and that's going to cause the oxygen to connect to the carbon. And so in covalent bonding, we have sharing of electrons. So it's kind of like the metallic bonding, kind of like that electron C model, except in the metallic bonding, all of the atoms shared all of the electrons. In covalent bonding, we're just going to have two atoms sharing a pair of electrons. Now we can have more than just one pair shared between these two atoms. In fact, carbon and oxygen, when they form carbon dioxide, will actually share two pairs of electrons. So it'd actually be another pair in here. And we'll look more specifically at how to draw that later. But we would have a total of 4 electrons shared between each oxygen and the carbon. But they are each individually sharing. So the carbon is sharing with this oxygen, and this carbon is sharing with this oxygen. And that makes this pretty rigid bond. It's going to be held in that specific structure. We're going to look at how to model out the shapes of covalent bonds later. But for now, we're just understanding that when we have covalent bonding, we have these electrons being shared. And because of that, we don't really have an exact specific way that covalent bonds go together. Like I said, I could have CO2, but I can also have CO. This is carbon dioxide. This is carbon monoxide. Carbon monoxide is very poisonous. Carbon dioxide in large concentrations could be poisonous too, but we breathe this out. We're around this all the time. But carbon monoxide, even in small amounts, can be very dangerous. And so we could have CO2 or we could have CO. Well, we could have things like NO2, we could have N2O4, we can have all of these different proportions of these atoms. And so covalent bonding, when we name it, is going to be looking at those specific proportions. And we're going to look at that in a few lessons. Compared to ionic bonding is going to bond exactly according to the balancing of these charges. Sodium and chlorine together, well, this is going to be a +1 charge and a -1 charge. So sodium and chlorine together are going to make NaCl, and it's always going to be NaCl. I can never have Na2 or Na2Cl. I can never have NaCl2. It's always going to be this exact ratio of 1 to 1. This is a 1 to a 1. Okay? So that's our different types of bonding. So let's quickly write those down, just to review a little bit. We had metallic, where all atoms share all electrons. And then let's put ionic underneath that, ionic. An electron is traded causing an ionic charge to form. And then those charges stick together. And then covalent, you think of that as being similar to both of these, but covalent is going to be one pair of electrons shared between two atoms. And in the next video, we're going to start to look at how to write ionic formulas and names. After that, we'll look at how to write covalent formulas and names, and they'll both have their own subtle naming structures.